Section 5.3 is on the law of sines, and 5.4 is on the law of cosines. In this video, I wanted to introduce the law of sines and discuss how we use it and why it's useful. Next week, we'll work on the law of cosines because I think this week's lecture is getting a little bit long, so wanted to stop at 5.3. And next week, we'll kind of wrap up this subject with 5.4. But the law of sines and cosines, just before we get into it, the purpose of these laws is to help us solve triangles which are not right. So as I was emphasizing in the previous videos with SOHCAHTOA, Pythagorean theorem, those only work with right triangles. If there's a right angle, SOHCAHTOA is cool, a squared plus b squared equals c squared, cool, does make sense. But if our triangle does not have a right angle, those formulas are immediately thrown out the window. Those no longer make sense. And the question is, how do I solve them in those cases? But that's kind of the purpose of these rules, is to sort of expand those formulas for a generic triangle. And while these formulas are a little bit more complicated, they're more useful in general because they work with not just right triangles, but any triangles. But one of my close friends is an architectural engineer, and he said that, really all you need is SOHCAHTOA because these laws really are just extensions of SOHCAHTOA. And if you know SOHCAHTOA, you could figure these things out too. But really, I think they're still very useful to know because they generalize the process to all triangles. And they're actually fairly simple once you get the hang of how you use them. So let's start with the law of sines. Let's just look at the law of sines, kind of explore how it works, some examples, and obviously, well, why is it true is something that I definitely want to focus on as well. So the law of sines states that in triangle ABC, we have sine A over A is equal to sine B over C. Sine B over B is equal to sine C over C. And remember the naming convention, which is common with these sorts of chapters on trigonometry, is that even when a triangle is not right, we typically use A, B, and C to stand for the sides and the angles. And typically A is the smallest side, C is the longest side, B is the intermittent medium side, but it doesn't actually really matter. You can choose any of the sides, but what is very important, like I said before, is that if you have angle C, that side C should be the corresponding side across the triangle. B and B should match up across the triangle, and A should match up. This is very important. You can't just arbitrarily choose ABC, ABC. I mean, you can pick whichever ones you want to be A, B, and C, but you have to make sure that the sides and the angles are paired up for this formula to work. And like another thing I wanted to mention is an alternative version, which you see up here or in the packet, which is how I believe our book, if I remember correctly, presents it, is just the same set of ratios but upside down. Notice it's really the same formula. It's just the fractions are reversed. But say imagine this is 2 to 1, 2 to 1, 2 to 1. It would just be 1 to 2, 1 to 2, 1 to 2. It would still be equal. So it doesn't really matter which version you use. I typically, I'm just used to using it in the form you see from the packet. But anyways. And so these formulas help us solve triangles which are not right. And we'll see how that makes sense and why it works in a minute. But for now, let's start off with an example just to sort of explore how this rule works within an actual triangle. I'm going to go ahead and end this slideshow and move to the whiteboard back to the packet here for a second. But in this example, notice that I've provided you with just a random triangle, which is not a right triangle because we have a bunch of sides and angles, but none of them are 90 degrees. But in this triangle, let's just kind of explore the law of sines to see what will happen. But what it says is that, let's just say I call this one the smallest side A. And again, little letters for sides, big letters for angles. Little letter, the longest side we'll call C, and the biggest angle C correspond. Also, another thing I wanted you to notice about this triangle is that when we're pairing up sides and angles using A, B, B, and C, notice that the largest angle corresponds to the largest side. The smallest angle corresponds to the smallest side, and the medium angle corresponds to the medium side. That is not a coincidence. That's just a property of triangles that must be the case because it's like, imagine a smaller angle. The side that is responsible for must be smaller than the side for a larger angle because larger angle means larger corresponding sides. So it kind of makes basic sense that must be true as well. And the law of sines is essentially, it proves that there is a ratio that holds up across the triangle that's inherent based on that particular idea. But it's not just a direct proportion, so they're really not proportional to one another. They're proportional with regards to the sines of those angles, which is why it's called the law of sines. So say, for example, we were to take the sine of angle A, which is 33.5, and divide it by side A, 5. Well, we don't really know what that would be without a calculator, but we could go ahead and calculate what this ratio would be. Sine of 33.5 divided by 5. And that's going to give me approximately 0.11. That's close enough. And so, well, what is that? But basically, there's a that sine has a particular trigonometric ratio, as we've been discussing. And if I divide it by 5, it's going to be even smaller fractions. So I'm going to get a little small decimal number for that. And so my point is, well, what if I go ahead and look at the sine of the medium angle divided by its corresponding side length? What the law of sines proves is that this has to be the same ratio as the previous ratio. And we can go ahead and confirm this. So I'm not really proving it to you right now. I'm just sort of showing you what will happen. But notice what I get is the exact same ratio, approximately 0.11, when I take the sine of the medium angle with the medium side. And if I go ahead and take the sine of the largest angle, 84.3, and divide it by the largest side, whoops, need to make sure to close off my sine, divided by 9 there, it's the same exact ratio. And notice it's not exactly the same because these angles were probably not exact values. They're probably rounded, which explains the minute differences in those law signs. But anyways, notice that we get the same thing. And why that's helpful is we can actually use that knowledge to our advantage to solve a particular triangle. It's sort of like how we use SOHCAHTOA to solve previous triangles. We can use the law of sines to actually solve a triangle. So let's look at an example, and then we'll come back and prove the law of sines before we do a few more examples. But say, for example, we're looking at this triangle right here. Notice that we're given that side A is 55, side C is 20, and angle A is 110. And actually, before I begin, this actually makes no sense, because if this length is 55, there is no way this length could be 20, right? Because they're like pretty similar in their measure. So if I was to go ahead and solve this triangle, the answers aren't really gonna seem very right. So let me just fix this. I took this example from somewhere. And let's just say that that's 42. I'm making up numbers here because it doesn't really matter. They could be whatever they are, but that 20 just made no sense if that was 55. So this is a little bit more. Again, these are random problems that I'm generating, and technically you could solve any set of sides with angles using the law of sines, but I wanted an answer that was a little bit more sensible to the given 110 degrees. And also notice that since I know this is 110, I actually can't solve either of these angles because when we were solving right triangles, it was always we could always find the other angle because we knew one of the angles was 90. But here I don't know that one of them is 90, so both of these two are still unknown. So really, I don't know any of the angles. Also, I cannot solve the third side right here because the Pythagorean theorem does not hold, because this is not right. So everything we were doing before is thrown out the window because there's no right angle here. But the law of sines is a way that I could solve this, because if I think about what I know, notice that I know A and A, both capital A and little a, which implies that I know the ratio of sine A to A, which is equal to sine 110 degrees over 55. But also notice that I know side C but not angle C, but I know that that must be equal to sine C over C because the ratio of the sines to the respective side, sine of the angle to the respective side, is the same across the triangle. And really, since I know side C is 42, notice this creates an equation with only one unknown. What I get is that the sine of 110 over 55 must be equal to the sine of C over 42. And basically, I'm using the law of sines to start off because they're all three equal. It's kind of like I'm taking two pieces of this equation to start. Sine A over A equals sine C over C. And this presents me with the equation with, well, notice there's originally 4 unknowns. Since I know 3 pieces of those, I plug in the parts that I know, and that leaves me with one unknown, capital C, the angle. And what I could go from here is I could multiply across by 42. Since this is really a proportion, that would leave me with 42 times the sine of 110 over 55 must be equal to the sine of C. And all of that would just grind into a bunch of numbers, so we could go ahead and calculate what that is. 42 times the sine of 110 divided by 55. And that must be equal to the sine of C. So sine of C is equal to that particular ratio. And then I could take the arc sine to find angle C. So C must be equal to the arc sine of that. Or approximately, because I rounded it. Or I could just take the arc sine of the entire answer from before, which would leave me with approximately 45.9 degrees. And anyways, notice what I could do is I could find the unknown angle by using the law of sines. So it's actually very, very similar to using SOHCAHTOA. With SOHCAHTOA, we start with, say, sine equal opposite over hypotenuse to solve a triangle. Here, we can't start with SOHCAHTOA because it's not allowed. It's not right. So what we have to start with is the law of sines. And basically, it's a formula where we can begin to find parts of the unknowns, and we could work out the remaining parts of what we know. And then notice once I find this angle, now I know 2 angles of the triangle. So the third angle is readily apparent by the 180 principle. So I know that the interior angle of the triangles have to all add up to 180. So if I subtract the 2 that I know that A was 110, and C I've now solved to be 45.9 by the law of sines. That would leave me with B must be 24.1. And I could then find the third angle. And once I have that angle, now the only thing that I still don't know is the side B, which is at the bottom. But once I find the respective angle, I could then use the law of sines to figure out what side B must be. So it's a pattern of using the law of sines, using the interior angle property kind of in a sequential order in order to solve the remaining unknowns for a triangle. And before we end this video, why is the law of sines true? So why, how do we mathematically prove that this must be true? Because what we saw is that it did work, but we didn't really prove it. So that's the last little bit for this video. And really, it stems from the fact that any non-right triangle can actually be broken up into 2 right triangles, and every observation is, kind of those formulas have been derived from that observation. But like, say for example, I start with a triangle ABC, which is just a generic triangle, any triangle which is not right. Notice that there should be some way that I could split it into 2 right triangles. And you might be wondering, if it was an obtuse triangle, you could split it a different way. There should always be a way to split any triangle into 2 right triangles. By taking one of those lengths and breaking it apart, using a perpendicular, not a bisector, but taking a perpendicular line to the opposing vertex. But in this case, basically what we could do is we could call this is often referred to in a non-right triangle, it's often called the height of the triangle. Like if we were imagining a building sitting here where the base of that building was side A, how tall the building would kind of be its perpendicular height value, which, in this case would take that building and bisect it into 2 separate right triangles. And basically what I could use is I could use observations about the sine, because notice that in each triangle the opposite side is the same length, and that's kind of where the law of sines comes from. Because if I look, for example, at the sine of angle B, that would be SOHCAHTOA opposite over hypotenuse. So the sine of B would be h over c by SOHCAHTOA, because this forms a right triangle. I know the sine of B must be that particular ratio. If I look at this triangle, the ratio of that sine would be, well, opposite over hypotenuse. That would be h over b for the sine of c. And so in both of these formulas, notice it relates the sine of b to the opposing side C and the sine of angle C to the opposing side B. But the key there is that the height value in both is the same. And the height here was equal to C sine B. The height here was equal to B sine C. And so those must be equal. So if I equate the height value, which has to be the same in both triangles, what I would get is C sine B is equal to B sine C. And if I divide both sides by C and B, divide this by C and this by B, that would give me with, I would divide that over there, divide that over there. That would leave me with sine B over B is equal to sine C over C, hence proving the law of sines for angles BC and side BC. And I could do the same thing by splitting up side A if I did a perpendicular bisector here, or let's see, or here. You could do the same thing to show that sine A over A is equal to sine B over B and is also equal to sine C over C by extension. So that's kind of the idea. And what's kind of an important conclusion to know about this is that the law of sines is always true for any triangle, and we can use it as a formula to solve them. In the next video, we will do some examples of using the law of sines, do more of the algebra and the math behind actually finding those values